Now, as I said in class, we are going to skip the rest of the C questions. Doesn't mean you shouldn't do them. You should work through them and see if you have questions. I'm going to skip the D questions, at least for now, because they're pretty straightforward. But what I want to move on to is the E questions on the January 14th document. And the reason for that is that one of the ultimate goals of this segment of the course is to understand some thermodynamics. And just to give you an idea, we could, if we heat the air in this bottle up, we could increase the pressure, and by increasing the pressure we could raise water and raise water to a greater height. Okay, of course it's Mountain Dew, but it's at this height, and we raised it to this height. Now we could have a reservoir at this height, and then the raised water could be lowered back to the original position, run through a turbine, and generate power. The point is that then we've increased the mechanical energy of the water by raising it. Its potential energy has been increased, and that increased potential energy could be tapped in one way or another. Now, I did that by squeezing the bottle, but you understand that that could have easily been done by heating the bottle as well. And we're actually going to do that sort of thing. Right now, what we want to do is start to get a handle on the amount of energy it takes to change the temperature in that bottle. And we're going to combine that with the gas laws and come up with a pretty good model of an engine that runs by heat, and hopefully gain a pretty good grasp on the basic thermodynamics of that engine. Now, the first question is, how many moles of air contained in 500 milliliters? And I'll say I chose 500 milliliters because this is a 591 milliliter container. If we fill it to about here with water, we've got about 500 milliliters left for air. You need to understand that. We want to know how many moles of gas there are in that bottle if it's at atmospheric pressure, which at our altitude is very close to 100,000 pascals, 100,000 newtons per square meter. So if I take this bottle and seal it, it's going to be at the pressure of the atmosphere here, very close to 100,000 newtons per square meter. And 300 Kelvin, which is a little warm for the room, but not an atypical or completely ridiculous room temperature. Room temperature is usually closer to 23, 24, 25 degrees. Celsius, 27 Celsius would be 300 Kelvin. So a few degrees warmer than typical room. Okay, well, how are you going to figure that out? You got that information, you have the E1 question, you should go ahead and work that out. Of course, I'm going to continue now. You should have paused and done that. So, 100 kilopascal, 300 Kelvin, 500 milliliters, 8.31 joules per mole Kelvin. How are you going to do this? What are you going to rely on? Well, PV equals nRT, gas law. It's fairly obvious. You've got a pressure, you've got a temperature, you've got a volume, and you've got the gas constant. Fits right in. You easily solve for N. So if you haven't already done that, you should do it without looking at what I've done. You're going to have to do a few conversions, make sure the units work out. Okay? You should pause and do that. Anyhow, okay, here we go. N is just PV over RT, that's obvious. We got 100,000 newtons per square meter for the pressure, the volume. Now, the volume is 500 milliliters. In advance, I know that 500 milliliters is half a liter. Now, why do I want to go to liters? Well, because a liter is 1,000th of a cubic meter. So knowing that this is half a liter, it's half of 1,000th of a cubic meter, which is 0.005 cubic meters. Why do we want cubic meters? Because all these, we have joules. Okay? Joule is an MKS unit, a standard SI unit that involves meters, not milli anythings. So we want the volume in cubic meters to be compatible with the joules. Now, in the denominator, we have the joules, we have the moles, Kelvin, degrees. That's our universal constant. We don't have to worry about that. Temperature is 300 Kelvin. If we do all this, and work out the units, which you need to do. I haven't done them here. And you should be able to work out these units without any problem. You come out with something that's pretty close to 0.02 moles. Okay, say approximately 0.02. Now, you're given information. Okay, the E2 question says molar specific heat of a gas. What do we mean by molar specific heat? We mean the amount of heat you got to apply to a mole to change the temperature by 1 unit of temperature, when the temperature changes, well, okay, it's the amount of heat energy you got to supply to a mole to change the temperature by 1 temperature unit, and that is given as 3/2 R. Now the question is, why is it that 3/2 R has the units that you would expect for a molar heat constant, molar specific heat? Well, it's the unit of R is joules per mole Kelvin. Okay, so that's going to tell you how many joules you got to do to change the temperature of a mole by Kelvin degree. Now that's not the constant. The constant is 3/2 R, as it says in the problem. So you need to use that information and the fact that air is a diatomic gas. It's almost all oxygen and nitrogen. There's a significant amount of argon, I believe 1 or 2%, something like that. But air is at least, I think, 98% oxygen and nitrogen. That's all diatomic. So air essentially acts as a as a diatomic gas. So we have a diatomic gas in here. We have a molar specific heat. We know we have 0.02 moles of air in this gas. And we want to figure out in the E2 problem how much it's going to take to increase the temperature of that air by 20 kelvins. So you should work that out. Okay, well, if you've worked it out, great. Okay, now I've got CV. That's C for specific heat, it's the usual letter we use, V for constant volume, and monatomic. So CV for monatomic gas is 3/2 R, and you can do the arithmetic on this. CV for a diatomic gas is 5/2 R. You can do the arithmetic on that. So the delta Q is the change in thermal energy, the energy you've got to add to the gas to heat it up. The heat energy you got to add 500 milliliters, increasing it by 20 Kelvin. You simply multiply the specific heat, the 21 joules per mole Kelvin, by 0.02 moles by 20 Kelvin, and get 5 joules. And if you had read that problem and interpreted it carefully, that would be a fairly obvious thing, and hopefully this just confirms what you already figured out.